Okay. Can you hear me? Is it okay with the mic? Okay. So thank you for inviting me. So this is actually a talk that is based on our vision paper that will be presented later at Spatial. But my goal here is to be a little bit less formal, to kind of share with you some of the process that led us to get into quantum, where actually I must admit that I and Divesh, who is my manager, we are kind of new to the area. But what happened is that at AT&T recently, quantum started to become a very interesting topic at different levels. There was a growing interest in the area, and we were kind of pulled into the area where what happened is that, again, managers and employees started to notice that we see significant improvement in the area, right? You all heard about it. And as we see this improvement, there was an interest to see what can that do to a company like AT&T. Where can AT&T exploit the advancement into technology? And what we started is to look from a higher level about what a company like AT&T can do. And we saw that there are different domains, including, for example, quantum computing in general, right, with usually circuit-based machines. There's quantum security, there's quantum sensing, quantum communication, and quantum optimization, where right now I would say that quantum security is by far the most resource in terms of how much resources the company is investing, mostly in quantum security. This is by far greater than all the other areas. But our goal was to look a little bit further beyond just what would be after, let's say, breaking encryptions like RSA and others. So our goal was to further look into quantum optimization. Okay, and the other areas, I wouldn't say that they are not important. Quantum communication is clearly very important for companies like AT&T. We are looking a little bit into them, but it seems at this point that they are a little bit further into the future. Okay, it doesn't seem that this would be the next thing, while quantum security and quantum optimization seem to be a little bit more mature, where we could gain benefits for the company a little bit sooner, I would say. And you all heard about the different approaches from quantum annealing or adiabatic processes, or if we work with circuit-based algorithms and we apply QAOA for optimization. So we have different optimization approaches. And at this point, again, for companies like AT&T, I can say about AT&T, we are exploring the different options in terms of the venue. So we are, I would say, as a company, and I believe many companies are like us, we are kind of exploring what would work. Okay, and this is a hard problem, okay, because it's not just about theory. We want to know what would work in practice. And again, I would skip here the whole issue of cubic formulation. You heard enough about that. But I would like to point out, and this is where things get interesting, I think, for the audience here. Networks are really complex. You know that, okay? And it's really expensive to build networks, okay? We have, in terms of telecommunication company, the problem of how to design networks and how to operate them. Now, operation is at different scales of latency. We are not even talking now about operation. We're talking about planning. But planning itself is at a very large scale. And what we see is that there's many optimization problems involved in planning networks. Okay, and many problems also have a very strong spatial component. That's why it's really interesting, where you can actually get hard optimization problem, high value, and spatial component. This is exactly the domain where researchers here can find many interesting problems to work on. And it's also very important to point out, and this is something that adds to the complexity, many of the problems are multi-objective problems. So you want to have networks that have high transmission quality. The cost should be as low as possible in terms of building the networks and maintaining them. They need to be very reliable. So now you have sometimes all kinds of trade-offs. And when you have these multi-objective problems, usually you can think about the Pareto front of those problems. And you don't always get to just compute one optimized solution. Sometimes you get a sample of the Pareto front. And if you do that, then of course you can see in already published work that many times in using quantum algorithms, people compute these Pareto fronts efficiently and sample them. It's much better than just trying to compute one solution or compute many different solutions. Okay, but the one thing I really want to emphasize here is that all these problems are at a very large scale. This is where it's kind of if you want a pushback or an opportunity, depends on where you are. One more thing I really want to emphasize is that there's a lot of study when it comes to optimization on the different complexity classes and where things stand. For us, I know that this is more like a practical point of view. We don't really care about the worst case scenario. Really want to improve things so that we would build better networks. And if in some places things are not as good, I mean, we want to avoid those cases, but we want on the average to have better networks. Okay, so that's very important for us. And to emphasize, one of the first problems we were starting to look at was the problem of fiber planning. Okay, this is a problem where we are actually investing at this point a lot of effort, where, for example, when we plan fibers, we start with something which is called a wire center. It's a large area where we actually can have thousands of living units there, and we need to deploy the fibers. I wouldn't go into all the details of how it's being done, but the result should be a tree that minimizes the total layout, the total length of the fibers, because digging is very expensive. Okay, and here is just an illustration how you can actually have. This is actually the points. The red points are places where we put something that is called. These are potential access points or FAPs, and then there are the living units, and what we get is a huge graph, and we need to solve some version of a Steiner tree, which is a hard computational problem. Okay, so it's a very hard problem, very strong spatial component, and when you try to solve it, here you can see some running using a solver, an ordinary solver. One thing we can see is that as we go from an ordinary representation, as we increase the number of possible points, in this case, you can see that even for a CPLEX, we move from 3.8 minutes to run the solver to 21.9 hours. But this is for a cluster, and there are hundreds of clusters in a wire center. So it's like we took a toy example, and even now, when we try to solve it, it gets like to 21.9 hours. So it just doesn't scale, okay? At least not on an ordinary solver. I would skip here here you can see some of the representation as a Steiner tree. But here's another problem, that when we try to represent the whole thing as using quantum representation, we actually get that the number of qubits is quite large, right? Here we have like, say, 68 qubits just to represent the tree problem. Okay, so I would, because I don't have much time, I would skip some of the other problems that are involved in network planning. But what I want to actually emphasize is that we have a large variety of problems, which actually can be represented, or to solve them, we need to solve hard optimization problems like Steiner tree problem, like minimum spanning tree with degree constraints, like set cover, like knapsack. And what we see right now is the large, very large gap between the number of available qubits and the scale of network planning. Okay, so this is actually a very hard problem. And again, the numbers are really big in terms of the network. We are talking about thousands of towers. We are talking about millions of miles of fiber. So these are really large problems. And the key thing is that, and I wouldn't go into the details, but the key thing is, are we able to apply spatial algorithms like partitioning, like clustering, right? And you can see, I would skip some of the formulation things as cube, but the question is, are we able to eventually partition the problem in such a way that it would suit a quantum algorithm, would give us some advantage on the one hand, but also will be small enough to suit the available qubits that we currently have. So again, I had to skip many details because I don't have the time right now, but I want to emphasize that eventually we have here very challenging problems, very strong spatial component, and the solutions to these problems are something that we really need at the industry. It can save, and I'm not exaggerating, billions of dollars. So these are really high value problems, and they provide a really great opportunity for research in this domain. Thank you.
Okay, thank you very much. So this is give a quick idea about very valuable type of contribution. Any quick question for Jan?
Try to start some experiments to deal with this issue. Yes, so I was showing something that where we are actually working on some of those problems. It's very hard because, as I was showing, even with Cplex, even for a small problem, we get into things that are very hard to compute. We right now have some implementation on a quantum machine using QAOA. We are working with IBM. The problem is that without any limitation of the problem or partitioning, we are not able to represent the whole thing as is. And I also want to emphasize there's something I didn't say. We are trying to solve tree problems. Tree problems are notorious in that domain because they are cubic, right? They're not even quadratic in their representation, at least in some of those cases. So things grow really fast. I mean, even if not exponentially, still cubic growth is really problematic, and soon you get to the point where you don't have enough qubits. So that's why we believe, we don't know for sure, that some spatial algorithms would allow us to work in a smart way that would limit the problem to domains where we can solve significant portions of the problem, but without the need to represent the whole model or the whole problem in entirety in one computer or with many qubits.
Okay, thank you very much. So
Thanks.
Let's move to the following speaker. Thank you, Jan. So Martin. Yeah, 6. So, okay, welcome everybody. I actually did not prepare the first slide, and the first thing that we found out is quite funny, is that the physicists, they like titles, right? So please remove the professor and the doctor here. I'm just Martin for everyone. But beyond that, what I want to show to you first is something non-quantum a little bit, because we have these practical challenges. So what are the practical challenges? We have just a few qubits, and they actually don't work very well. We have a lot of noise, so our algorithms should hopefully correct themselves if they can. So in a sense, yeah. And we still want to have this exponential representation power, but we can't trust it. And we have a classical methodology of computing that is actually the same as the randomized algorithms, right? So very simple data mining case, you want to have the eigenvalues of a very, very big matrix, and you don't have time for it. So you look at some random submatrices, maybe 10, and you look at the eigenvalues you get from these 10 by 10 submatrices, and most likely you will see the same eigenvalues pop up again, and then you trust randomized linear algebra that this is the eigenvalue of the overall matrix. This is actually how you kind of do movie recommendations efficiently. And we want to do the same with spatial data. So the first thing I show to you is just binarized encoding. So we are doing image classification like MNIST, but even smaller because of quantum computers. So this is a digits data set. And when you look closely, then you see these grayscale values. And we can just say, okay, to some extent, all the versions I can write a 1 to is a random distribution. Yeah, these are the grayscales, actually. It's something that we can try to do. And here we just go and look at it, we binarize it, and we encode it. We encode it in the classical superposition. What do I mean by that? We take something like a hash function to a very small bit array, and then the same pixels, so 2, 3, 4, 5 different pixels, go to the same one classical bit, randomly in superposition. Okay, we destroy a lot of information, so the question is whether this actually works. And next slide tells you, yes, it does. So here we see that we take these images, 16 by 16 pixels, and we don't have 16 by 16 qubits. So we just hash them to a bit array. It's just randomized now. It can be good or bad, depending on whether I'm lucky or not, but when I try often enough, I'm lucky, right? And here you see that kind of this is both classically and quantum-wise a very interesting thing. Mira and CC are two different quantum circuits. You can look into our papers what they actually do, but these are two quantum circuits, and they work very well. And the support vector machine and decision tree are super classical algorithms, and they work as well. So what we did essentially is we used randomized algorithm in order to bring a 16 by 16 matrix to a 4-bit array, doing lots of errors, but doing this often enough in order to ignore the randomized error and get a real result. That's fascinating. And we took this even further. We said it's very unlikely that all interesting problems can be compressed by random transformations to 4 bits. Yeah, that's not very likely. But if I look into different bits, it works. So we take our input data, we take some sort of bit array and some sort of hashing to it. The bit array can now be large. And we just look into random projections of this. So linear algebra from the 1950s, 1960s in computer science, this was kind of a classical thing. You say, again, in order to do something, I just don't look at everything because I don't have time for it. I look at a random sample, and as it's a random sample, I do this more than once, and when I'm lucky, I win the game in the end. This works for quantum algorithms as well. So by applying the same quantum algorithm, so it's the same configuration of the QUBO, just changing some of the data encoding, we can actually get the final result. And if you don't trust me, you can look into the experiments. They are really ugly. You see here for kind of detecting digits, you see kind of a 60% performance. That's not really nice, especially not for such a simple data set. But even the final models can be ensembled again. The point is here just the randomness. So I'm doing it just wrong because I expect it to be wrong. Most of my samples are wrong. But when I do it often enough, which then, of course, slows down our algorithms, I have to be fair, we get to this 95% boundary, and much more we cannot actually expect. So the point I want to make is that quantum computers are really, really small. So we need to put them in an environment as a coprocessor where we can formulate large problems. and use partial solutions successfully, very much like your partitioning approach or things like that. And this is where quantum and classical algorithms meet. And randomized data structures, I do this since a few years, they remain fascinating to me. And that's all from my side. Do you have questions for this part? Otherwise, I let Carla take over for the quantum database perspective.
So hello, I'm Carla. So I was working on this project regarding quantum databases together with CERN and Intel research, and together we were thinking about how feasible it is to transfer classical database operations to the quantum domain, specifically large superposition states. So as you've heard today already, you know maybe about Grover's algorithm, which is a search algorithm for unstructured. Okay. So you heard today about Grover's algorithm, which is a quantum algorithm for unstructured database search. And if I have an unstructured database with n elements, in the quantum scenario, I can get a quadratic speedup. And kind of this, yeah, the thought of the database itself led us to think more, starting from Grover, how we can see databases and generalize them in the quantum domain itself. And our main research question then was to think about the feasibility of transferring classical database operations to the quantum domain for specific quantum states that I will show in a second. And then another question regarding this is when we, for example, look at the reserve operations for classical databases, like an extension mechanism for databases, we thought about the question of how we can integrate quantum computers into a real-time dynamic data processing workflow and a data processing chain, so we can accommodate for time series that can be initially of unknown length, which I recently presented at the IEEE Quantum Week. So taking one step back, generalizing databases. So in this chart, we see also our kind of classical database domain here in this fragment here. So generalizing databases to the quantum domain, we thought about the type of indexing and the type of data that we can have, which can be both classical or quantum. So here the C and the Q. And especially for the databases here, for our quantum databases, we think about the quantum indexing part, where we can have indices in superposition. So we can have individual data elements in superposition, in a superposition state, which looks like here, which we will see a bit in a second. So if we have classical indexing, today we've seen a lot of states in Dirac notation. So basically, we can have individual qubits or a set of qubits encoded in this Dirac state, and each state that lives uncorrelated next to each other is in a tensor product. So basically, these are vectors. They are combined through a tensor product. And if we have a superposition state, we have a linear combination of our individual states. So for example, if we have n qubits, we can have our Hilbert space is exponentially large in the number of qubits. So we can have 2 to the power of n basis states in our Hilbert space. And we could have, for example, in the computational basis, all of them in superposition. And so this is basically the index subspace that we can span. And we can leveraging the exponential size of the Hilbert space, we can exponentially compress our data and represent it in this parallelized and superposition form. So with respect to our quantum indices, which is a dedicated register basically in this quantum database structure, we can correlate data to it. And basically, here we have k elements. You need to think of this k as being for n qubits, k would be 2 to the power of n. So we have an exponential number of elements in superposition for n qubits here. For our algorithms that we developed in this context, we focused on a specific database, specific state with a given amplitude, which is here uniform. So we can have a set of algorithms that mimic the classical database operations in the quantum scenario. I just because the talk doesn't have much time, I just selected the first interesting algorithms for this is, of course, what we always need to think of is initial state preparation, which needs to be efficient. So we can't have a too deep circuit. It needs to be at least polynomial scaling to be considered efficiently in the in complexity theory. We need to have an efficient data reading process into our state, which is now this quantum superposition state that we're considering. And what I'd like to focus on now is this reserve operation. So reserve in classical database scenario would be, we call it now extension mechanism in the quantum database scenario. So what we did in this work was to extend the index subspace. So we correlate new qubits to this state, and we'd like to extend so the amount of indices in the superposition state in order to accommodate for new data read-in. So we can have new resources allocated for future data read-in, so we can process basically time series during an online update process. In a more general, so I'm not showing any more quantum states, because the talk is really, doesn't have so much time. So in the general mechanism, where we can use the extension mechanism for quantum states would be in a, for example, experimental workflow where we can have data that can be, for example, also classical data encoded in quantum states, but also data stemming from an experiment, a quantum sensor, so anywhere where we can have quantum states. And during an experiment, we would extract data at a time step j, and we can read in this data into our quantum processing unit and update the quantum state on the go in quantum software and accommodate for new resources on the go. This could iteratively be repeated, and after some time, we would like to finish the experiment and extract global properties from our state. And because of the superposition that we have, this is quite nice to leverage quantum parallelism for global property extraction. So I'd like to quickly highlight kind of the update mechanism that we developed. So, but on taking one step back is again the state preparation, for which I'd like to quickly mention the quantum random access memory that also came to that we came to talk about today earlier. So the quantum random access memory, or this QRAM algorithm, this initial work I mentioned here names this algorithm called bucket brigade architecture that implements basically this transformation. So basically, upon providing a superposition of indices, so we have k elements here in superposition, the QRAM is a dedicated hardware structure that allows to read in the data in the superposition. So for each j in superposition, we return our data element in dj in superposition. So how you can think about this here is this in this bifurcation graph structure. Basically, this hardware structure that's presented in this work implements like these switches, these qubits that guide to the memory cells. And this bucket brigade architecture allows one to use only a polynomial number of activated switches during the process, and that's why it became so famous during this time. The problem is the physical realization of the QRAM. And another thing is it's really difficult to transfer this dedicated hardware structure to a gate-based form for a gate-based quantum computer while maintaining the advantage of this polynomial scaling here. So for our, I don't have a specific slide for this, but for our algorithm, we developed an efficient, so polynomially scaling state preparation algorithm for preparing this quantum database state. And on the other hand, we also developed an extension mechanism that's also efficient. So efficient, I mean polynomial scaling in the gate count. So mainly focusing on the C0 gates, because these are disentangling gates, the 2-qubit gates, which are hardest to implement, and also the circuit depth, because in order to have an efficient algorithm, we need a polynomial scaling in the circuit depth. From complexity theoretically speaking, because practically, of course, polynomial doesn't mean that we can directly execute it and utilize this algorithm immediately. But this extension mechanism here that we developed has basically two steps, which kind of showcase how operating on quantum superposition states is inherently different to operating on classical data, because on the one hand, as you mentioned earlier, we have the restriction with the no cloning theorem, so we can't have a general unitary that clones quantum data. And on the other hand, during process, we can have entanglement creation, which restricts our abilities that during our algorithm run. So we developed these two algorithms that need to take into account all the restrictions that we have when operating on quantum data, so no clonable data. And and this algorithm implements basically this update mechanism of our quantum state, and lets us kind of into this direction of doing online updates on the QPU on such a superposition states, but also highlights the inherent limitations that we have when operating on quantum data. So yeah, this was basically. Thank you.
Thank you very much. Any questions for Carla? Okay, so go ahead.
Good question. Right now, do you feel that these mechanisms would work better for classical, like replacing classical databases, or is it something where you could even gain more if you would actually have a database to support quantum algorithms?
Here, kind of the main question was how transferable are the classical database operations on quantum superposition states. And kind of what came out of this research are kind of guiding principles that show the inherent restrictions that we have in operating on quantum data in superposition, and what kind of we should do in order to have an efficient, for example, extension mechanism. So we need to allocate like in kind of in bunches, because basically every time we correlate a qubit, we double the amount of indices in our superposition, and also especially the no cloning theorem is an inherent restriction where it's really inefficient sometimes to read in data. So this needs to be done really carefully. And on the other hand side, it's also important if we know how to recreate our data, or if we kind of forget during an experimental workflow, because our quantum data could be only available at the time in an experimental schema, for example. And in this case, we would need to plan ahead basically and allocate amplitude in a reservoir and transfer this during the process, like in the schema. I just showed really quickly, but kind of these guiding principles on the feasibility. This was our main question of.
Maybe to put this into very simple words, as soon as you do quantum experiment with a quantum sensor, there's no way to store an observation. There's just no way, because in the moment you measure, it's gone. But if you can kind of keep over a long experiment a trace of everything you had so far, you have an oracle. At one time, you can measure and you can conclude a global condition. Yeah, it's really just you cannot store quantum data. That's kind of the point, and therefore we have the quantum database that keeps it for some time in order to allow at least one operation. Afterwards, it's broken because we measured. Yeah, so it's the same, but this was an unsolved problem, I would say, how you deal with quantum data actually when you don't generate it from classical data. When you generate it from classical data, it's trivial. You can recreate it. But when it's already quantum, you have a problem here.
So the question was, if you start with classical data,
yes,
with your approach, would you still gain any benefit?
Yes, because the state preparation takes 90% of your quantum computing. So if you want to, if you think about it like um, there's this forgetful operation inside in the database. Yeah, so we use our uh, auxiliary qubits for operations, and we feed in one after another. It's very similar to data re-uploading. That's also kind of such a pattern where you say, instead of putting all my data in parallel to the quantum computer, making it big, I use the same qubit over and over again to show some data. It goes into that direction, that in the end, the total circuit length is smaller.
This could be also then relevant in the future when multiple users, when the quantum computers grow and multiple users have access to the same device at the same time,
Yes.
and resources need to be distributed and allocated during the process in order to be
In
dynamic in the
supervision.
sense. Yeah, in a shared scenario.
Okay, good. Any other questions? Okay, thank you very much, Carla, again.
Thank you.
So this concludes the lightning talk today, having ideas about several different use cases people use with quantum. We were supposed to do a brainstorming session right after, but we had a very crowded program. So if we do it, we have to skip the quantum lab, showing you the actual quantum computer of DWAVE and how to encode on it and so on. So just to make it as a follow-up online, maybe also people who are interested in attending other workshop can join us. We have recordings here, so they can follow up with our recording and join. You know, some people work with routing, optimization, all of this kind of thing could benefit from quantum. So please, when we send invitations for this follow-up brainstorming session, try to attend. We'll try to make it in a time that fits different time zones, hopefully. But this will be very beneficial to write down notes, what we think. You attended today a quantum workshop, you have seen different use cases, you have some experience, different levels of experience. What you think Sega spatial researchers could do ahead, what are the opportunities? There are a lot of discussions and ideas came with the tutorial of the quantum gates, with the different use cases with Catherine. So we have notes. If we write these notes and put them in the proceedings of the workshop or Sega Spatial newsletter or whatever, as a record, as a roadmap, so Sega Spatial community can build capacity and engage more in quantum research in the future.